Can we start? So anybody from the organizers? I think this is okay. 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 So first of all, let me welcome you all for participating in this event, which is being organized by Chemical Engineering Student Society, NIT Durgapur. And I am very fortunate that they have given the scope to me for interacting with you on this particular subject. So let me, before beginning, say a few things that CFD, that is computational fluid dynamics, is a vast course. It's a vast subject. Okay, and even if you learn quite something of it, maybe the entire 1 or 2 coursework is needed. And what we are intending here to give you just glimpse of the CFD, that what are the basic structure, how it can be done, it can work, where it can be applied, what are the advantages, and little bit of technical things that we will cover. And the course content is actually targeted towards the undergraduate students mainly. Okay, CFD is generally it is taught at postgraduate level, either MTech level or in PhD coursework. It is taught, but nowadays our technical courses are advancing, so even the BTech students can have some knowledge of CFD. It can be helpful for them in their future activity. Okay, so with that objective, we have planned this course that undergraduate students can get a glimpse of the CFD. That means it's a specialized application domain of fluid mechanics. Okay, where your theoretical knowledge can be deployed to practical applications, and you can do a lot of things. So that glimpses you will get. And I can see in the registration list that a lot of first year students have participated. I am sure they have not learned fluid dynamics yet. So for them, how much it will be effective, I don't know. So someone is raising hands. I think, can you please? So
sorry,
please.
by mistake, please continue.
Okay. Okay, so so with these big things, let us start. Let the session be interactive. If you have any queries, you can raise hands or you can write the questions in the chat box, or so that we can have discussion. And I will now share my screen. All of you just check whether if it is visible to you properly or not. That you need to see. Just.
Hello, sir.
Yes.
Sir, actually, there is a problem in internet in hall 14, sir. So the connection is very bad here. So sometimes we can get out of the class and then like it will be a problem for us. So what should I do?
What should you do? That is my question also. If internet is problematic, we can try one
There
thing.
is huge problem.
I understand there is some network issues in some of the NIT hostels right now. So what we can do, we are recording this session. I think the organizers are recording it already. So maybe we can I can personally create a YouTube channel and give the link to you. Okay, so that the points that for portions you will miss, you can later on check it. Is it okay? I think that is the best thing that we can do in case of network discontinuity. Okay, so that we will try. I will talk to the students and that can be arranged. And I am just stopping the video so that the connectivity will remain okay from here. Just check if you can see my PowerPoint slides. Is it visible to you?
Yes, sir, it's visible.
Okay. So if any point of time, if there is discontinuity from my side due to bad network, just point out to me in my WhatsApp so that I can again start. Okay. So let us begin. What I kept the theme of this workshop is like ABCD of CFD. Okay. Because what we are going to learn in this workshop is very basic things and targeting to the undergraduate students mostly who have little bit of knowledge of fluid mechanics. Although CFD stands for fluid mechanics, note that it is equally applicable for heat transfer, mass transfer applications. Okay. Traditionally, since this subject was developed based on the solution of Navier-Stokes equation, so it is given the name CFD or computational fluid dynamics. But the method that we learn is equally applicable for heat transfer problem, for some mass transfer problem, and many more other applications. Even apart from chemical engineering also, if you go to the civil engineering part where structural mechanics, and if you go to electrical engineering, there are maybe some equations related to that. So the methodology will be remaining same. Okay, so it has, although it is the names is fluid dynamics, it is the methodology is applicable to various areas. Okay, not only limited to the fluid dynamics domain. So, uh, this is what, and next I will show you how I have planned this particular course, the contents. It will be covered in 6 lectures of 1.5 hour duration, and mostly it will be organized in the weekends starting from today. But next weekend we can cover 2 or 3 classes. Okay, tomorrow there will be no class, so timing will be notified to you. And the first class will be all about introduction to CFD. Okay, so this is this will clarify you that what is CFD, why we should learn it, what are the areas of applications, and what are the prerequisites for learning this subject. So that thing we will deal in the lecture number 1 today. Lecture number 2 will be dealing with the governing equations, different type of governing equations, and the discretization methods, and how to solve linear equation, etc. So we will discuss in detail later on. Third lecture will cover finite volume method and application of 1D heat conduction equation, convective equations, etc. So there you will get the feel that how mathematical equations can be modeled and you can generate some fruitful results. Then in the 4th lecture, we will try to introduce introduction of ANSYS Fluent, which is a commercial software for CFD, which is a well-known, well accepted by both academia and industry. Then in the 5th lecture, we will try to cover some of the basic elements of CFD solver. Okay, so gridding detail, meshing details, etc. And 6th part will be little bit more technically deep, that will be related to pressure velocity coupling, simplex method, under relaxation of flow variable, solution convergence, etc. So those things we will take. And 7th lecture is basically optional one. Here we will give some introduction about OpenFOAM, which is an open source code. Okay, open source code means it is freely available. Even the code can be accessible. In commercial solver, you cannot get the access to the code, but OpenFOAM is freely available. But it needs little bit of Linux environment. Means you need to have know little bit of Linux commands, etc. So that's why that is a separate lecture which you can take later on. Those who are interested can participate in that. But first 6 lecture will give you a brief outline about the CFD. Okay, so let us start with this first lecture that we are covering today. Going to cover today is all about Introduction to Computational Fluid Mechanics. Okay, so this is the basic course, and this, if anybody is working in this domain, if anybody has a little bit of knowledge, so for them it is just a repetition. But those who are completely new to this subject, for them it will be helpful to get an idea about the total concept of CFD. Okay, so what are, before beginning the things, let us see what are the prerequisites. Okay, so for learning this CFD, what you need to know. Okay, so that is here the first thing that is important is the knowledge of fluid dynamics and heat transfer. So knowledge of fluid dynamics and heat transfer and a little bit of transport phenomena. Although transport phenomena is mostly taught in chemical engineering curriculum, it is not generally taught in mechanical engineering, etc. But fluid dynamics and heat transfer is covered in most of the engineering discipline. And here the important thing that you should know is the different types of governing equations that are involved with fluid dynamics and heat transfer. Okay, now in this fluid mechanics or heat transfer courses, you must have studied lot of equations, and there may be many equations which are empirical and semi-empirical in nature. That means in a particular system, some researchers have worked, they have generated experimental data, and they have attempted to give some correlations. Okay, so that we encounter in these courses in the form of different dimensionless number, like in heat transfer, Ditas-Boelter equation, Seidel-Tate equation, in fluid mechanics, Bulk-Prammer equations, okay, Argan equation. So there are so many equations which are empirical in nature. But CFD will start from the very basic governing equation, which is obtained from the differential equations. And if we apply the knowledge of conservation laws, you know that the conservation law means input minus output will be equal to accumulation plus generation. So that is a standard form of conservation equation that we apply in different systems considering a particular volume element. And if you apply these conservation laws on particular domain, you can develop a number of partial differential equations, okay, or differential equations. So that are the starting point of this CFD. Okay, so we need to know, we need to have fair idea about the governing differential equations that are available in fluid dynamics and heat transfer. Okay, so that is why this knowledge is important. And first year students, those who do not have covered it yet, they may correlate whatever we are talking in future when these subjects are taught. Second thing is that knowledge about numerical methods. So this is also important. So numerical methods, at least little bit of knowledge means how to solve nonlinear equations, how to solve a set of linear algebraic equations, how to solve initial value problem or boundary value problem. So these are required for understanding. So if you don't have any numerical background course, grasping the concept may be little bit difficult. Okay, however, we will try to give the broad outlines in this course. So knowledge about numerical method is essential, specifically how to solve nonlinear PDEs, set of linear algebraic equations, etc. Third thing is that a little bit of coding skill, if you know. Generally, all the engineering courses in first or second year, we have some computing lab. Okay, where little bit of coding we learn, either C or Fortran or any other language we generally learn. So that is needed. Little bit of coding is needed if you like to go forward. Then fourth thing is that you need to have an interest for handling software. Okay, so this interest or learning learning appetite. So that is very important. So you need to have that thing. So if you have that interest in your mind that you like to learn these things and you don't have any allergic to the softwares, then you are welcome. Okay, so this is needed. And finally, an analytical mind is required because this is all about data handling. Because all these simulation will produce huge amount of data that you need to process, you need to analyze, and you need to find out the meaning out of it, the meaning out of those results. So that requires analytical state of mind. So these are the prerequisites. So if you are having these things, you are already on board.
Sorry to
Yes.
interrupt you, sir.
Yes, yes.
Sir, a lot of the attendees have been asking that whether they need to install any software. So, if you could inform
I'll
which
let
software they
me
should install.
yes, let me finish this lecture. Everything will be clear. Okay, what has to be done
Yes.
and what
Okay, sir.
not. Yes.
Okay. Thank you, sir.
Okay. Okay. So for the time being, just listen to me. Okay. Don't worry about that. Whatever needs to be done, I will tell in this class. So let me begin before introducing the CFD part. I like to give little bit of introduction about the different scales in simulations. Okay, scales in simulation means in engineering science we have different length and time scale. Okay, so phenomena takes place at different length and time scale. Length and time scale means, for example, if you are observing a chemical reaction, okay, you are studying or investigating a chemical reaction. So what is happening in a chemical reaction? Some bonds are broken and some bonds are being formed. Okay, and you are getting some product, right? Now, can you imagine that at what length and time scale that thing phenomena is happening? Can you have any idea? So, uh, can anyone give me idea that this molecular movement that happens at what length and time scale? Okay, let me answer. Yes, yes.
Nanoscale, sir.
It is far beyond nano. Okay, even nano is 10 to the power minus 9. But actually molecular movement takes place in femtosecond order, which is 10 to the power minus 15 second. Okay, so that is the time scale where the molecule actually collide with each other, bond formation takes place. So you can imagine, so even nanosecond is far ahead of it. Okay, so this if you look this graph, this is plotting time scale versus length scale. This is nothing. This is a dimension of length and this is dimension of time. So length scale starts from, you see that even we are starting from 10 to the power minus 10. This is a not a very scale, just a schematic diagram. 10 to the power minus 10 or below it. So this is the domain where the atomic interaction takes place. Okay, atomics means even subatomic. That means electron cloud exchange, etc. That will take place. So this is the domain where quantum physics or quantum chemistry is dominant. Okay, so high certainty, uncertainty principle, etc. Lot of things will work. So this is the quantum world. So where phenomena takes place at a very small length and time scale. Okay, this is the extreme bottom end of the simulation. So if you like to investigate some phenomena there, that how a bond is formed, how a transition state is formed, etc. So you need to do some quantum based calculation. Okay, so governing equations will come from quantum physics. Okay, and at the extreme top, that means this particular domain, which is known as continuum domain. Continuum domain means we assume that the property of the materials like density, etc., are a continuous function of the space. Okay, although the systems are made of atoms and molecules which are discrete particles, we are choosing the volume, control volume in such a way that your density will be remaining constant. It will not vary. Okay, so if I the concept, if I like to mention you, let's say you have a box like this. Okay, the reality is that this box, let's say it's a gas mixture is there in this box. So what it is, it contains a number of gas molecules or atoms, whatever. So if I plot a density of this box along this direction, along this length, rho is the density and L is the length if I plot. And if you consider this atomic existence, so what will happen? So you will get a very fluctuating plot like this, right? Because at some distance you will get an atom and some position there will be no atom. So there will be a fluctuating plot like this. So this is a discrete phase. But in continuum assumptions, so this is applicable here actually. Okay, in this quantum domain, this discrete existence is possible. Whereas in this continuum domain, here we are assuming, this is an assumption, we are assuming that if you have a box of gas molecules or gas, we are assuming that the density with this length is remaining constant. Okay, that means this control volume, you choose this control volume in such a way so that these atomic fluctuations are negligible. Okay, so average density will be remaining constant. So your rho will be remaining constant. Okay, so similarly rho, any other material properties, viscosity, surface tension, so all will remain constant along the length. Okay, so this is called continuum assumptions. And whatever equation, fluid mechanics equations we generally study in the fluid dynamics or transport phenomena courses, those are based on this continuum domain. Because you know we use differential equations, and differential equations are valid only for a continuous functions. So if your density is continuous function, then only you can apply them. So your CFD stands here in this domain. Okay, so CFD is applicable only at this domain which is beyond this 10 to the power minus 4 meter and above. Okay, so in this domain only your CFD will be applicable. If you go to the very atomic world, this is not going to work. Even if you go to this 10 to the power minus 10, 10 to the power minus 6 domain, this domain, okay, here also assumption of continuity will be not valid. Okay, so you cannot apply very frequently in a nano world. Okay, in a nanotechnological domain where phenomena is taking place at the nanoscale, it may not work. These governing equations will not be valid. Okay, so before beginning, I just like to point you out that our CFD or continuum mechanics will be valid only in this domain, only above certain length scale and certain time scale. Okay, so beyond which we cannot do these things. But fortunately, our world is the world that we can see as a human being, or our perception is there. So what we see in surrounding us, all of them are mostly based on continuum assumptions. You see that my chair, my table, my laptop, computer, everything is in the density is continuous. Okay, so we are not bothered about this atomistic world. Correct. So what we will do, our governing equations will be in this macro scale. Okay, in this macro world, we will going to solve our equations, and that is all about the CFD. So with this introduction of different scales, now let us move to the next one, which will show you the introduction to fluid dynamics. So I assume that all of you except the first year students have studied fluid dynamics. So what you have studied there, you have studied in fluid dynamics some of the analytical, empirical or semi-empirical laws or relations or correlations to solve some practical flow problems. So what you did, so you have studied, for example, Hagen-Poiseuille equation for calculating pressure drop. Okay, or you can Darcy's law for a packed bed. Okay, or many analytical or empirical relationship you have studied in this subject, and some of these equations that we use to solve fluid dynamics problems are continuity equation, momentum equations, energy equations, which are based on conservation laws. Okay, so those who studied the fluid mechanics and the transport phenomena, it will be clear, because in transport phenomena course we always formulate these problems from conservation laws and come out with continuity equation, Navier-Stokes equations, etc. So that is a part of fluid dynamics. Then the solution of the problem generally consists of calculation of velocity, pressure, density, temperature as a function of space and time. So this is so why we read fluid dynamics, because in many of the applications our interest was to calculate the velocity field. Okay, so what is the velocity at any particular so let's say if you are taking a pipeline, so your interest will be what will be the pressure drop in that pipeline, okay, and what will be the velocity profile at a particular cross section. Okay, so if it is multi-phase flow, let's say gas liquid is flowing, then what is the void fraction? Okay, then even in multi-phase flow, different regimes are there. Whether that is Taylor bubble regime or it is some homogeneous mixture type of flow. So there are many regimes are possible. So our objective is to understand that what type of flow profile is there, what is the velocity field, what is the pressure distribution in that field, what is the density distribution in that domain, and what is the temperature distribution. And this domain actually vary according to the space, okay, along the space. Okay, so if you take a pipeline, let's say if you are considering a pipeline like this, so if you're if your fluid is entering from this side or it is outside exiting from the other side, then you may be interested that what will be the pressure drop from this point to this point, what is the velocity at the intermediate domain. So what is how the velocity is changing along this length, or if it is an unsteady problem, how it is changing with time. So that will be our interest. Okay, so that knowledge fluid dynamics gives us. Now the equation, that is conservation laws, is combined form of mathematical expression that is represented by Navier-Stokes equation, because whenever fluid flow takes place, you know that momentum transfer, we actually are interested in the transfer of momentum. Okay, so that actually helps us to build a famous equation which is known as Navier-Stokes equation, which is a mother equation for most of these CFD type of problems. Okay, so how to formulate those problems, those equations, and how we can generate them, that comes from the knowledge of fluid mechanics. Okay, and I am assuming that one fluid dynamics course all of you have done. Still now we are just discussing general fluid dynamics. Now, what are the approaches to solve a fluid dynamics problem? So in industry or in nature, everywhere fluid flow is inevitable. You can see fluid is flowing in different forms. Okay, whether it is air, wind flow, or it is some water flow through a river, through a channel, through a even sewage line, and in domestics water supply line, everywhere. And in industry also, most of the units are connected through the fluid flow. So, yes, any question? Okay, so so there are three approach which is available to us to solve such fluid dynamics problem. Okay, the first one is experimental, the route of experiments, which is the mother route, I would say, because nothing can replace experiment. Final validation will always come from experiment. You need to do some rigorous experiment to find out the data. So whatever you like to know, whether it is velocity profile or pressure distribution or temperature distribution, whatever, you need to do some experiment in the lab. Okay, so that is the most vital part, and that is what in the last 200-300 years of the history of science, you will see that experimentation has always taken the final step. Now, what are the advantages? Because it is capable of being the most realistic method. Okay, so if you can prove something experimentally, nobody can deny you. Okay, because you have, that is the validation that you are seeing the results. But what are the disadvantages? Because all the routes have some advantages and disadvantages. And if you look here, for performing any experiments, you need to set up some equipments, some measuring devices, some instruments, etc. And the problem is that whenever your system is a very large scale, it is very difficult to do some experiment. For example, let me take an example that you are doing some design of an air vehicle, that means any aeroplane or aircraft you are designing. Okay, so is it possible that, and you will need to improve the design of the aircraft. Okay, so and you know that fluid dynamics is a very important part in a flight of an aircraft. So you need to do an experiment, obviously, if you like to do some design change. Now, how to do it? You have to build an aircraft first with your new design, which is a very costly affair and time-taking affair. At the same time, if your design there is some fault, the entire money that you are investing in that experimental studies will be lost. Okay, so that is why, and there will be some measurement difficulty also. So if you are trying to generate data from a supersonic flight, so you cannot, it is not so easy to get that kind of data experimentally. And operating cost is also sometimes high. Okay, so if your setup is quite expensive, its operating cost sometimes goes up. So these are some of the disadvantages, which are not disadvantages, these are the limitations. Okay, so which will not allow you to do experiment with all the cases. Okay, your time will not permit, your resource will not be permitted. So experimental route, that's why, although it is the last word, but you cannot afford all the time doing experiments. Then comes the theoretical route. Theoretical route means you will see that in most of our textbook, we deal with these kind of theoretical concept. So what advantage is there? So you can get general information in formula form. So you can build an expression in mathematical formula, you can or one equation you can develop and you can solve it. But disadvantage is that it is restricted to simple geometry and physics. Okay, so some of the you will see that in most of our textbook cases, we are taking that your pipeline is circular and otherwise your flow domain is rectangular shape. So that all different kind of simplification we do, but which is not the reality. In real life scenario, you will see that your geometries are much complex. It is not always circular. It is not always straightforward. It has lot of bends, lot of curves. So everything is available, which is very difficult to account in a theoretical analysis. So the third option that is available to us is the computational route. Computational route advantage is what that you complicated physics, even if there is a complicated physics, you can handle it. Okay, you need not do a lot of simplifications which are not permitted, and you can get details of flow. And the CFD that we are going to learn will belong to in this computational route. Okay, definitely there are a lot of computations who are involved, and that is why before the advent of the computer means the computer becomes available to the researchers or the academic community only after 1990s. So before that, it was a very limited scope was there. Although 70s, 80s computers were developed, but it was not available. So at that point of time, these subjects were not so developed. But the industrial setup, the process industry, chemical industry are set up were designed even at that time without taking help of any computational analysis like this. Okay, so those are based on some analytical design, Okay, but based on the intuition experience, they have designed those setups. But after 1990s or 2000 onwards, computers became less expensive and it is available to the students. And big computing power is in our hand right now. Okay, so we can deal with lot of complicated physics, and the results that we get for such kind of computational analysis is very detailed. Okay, so you can get velocity at each point, you can get temperature at each point. So that kind of data you can generate, which is very difficult otherwise to means by experiment or by theory. It is not so easy to get. However, disadvantages are there because in most of these computational methods is relying on the numerical approaches, which has some truncation error, round of error, and obviously computer costs and setting of proper boundary conditions. So these are some of the limitations which are associated to this computational approach of solving fluid dynamics problem. Okay, so CFD comes under this particular domain to solve fluid mechanics problem using the root of computations. Okay, so let us now understand what is CFD. So you get the understanding about the fluid dynamics, what fluid dynamics can do, because fluid dynamics is everywhere in natural phenomena, even in industrial setup, fluid flow is everywhere, and we need to get some data. Okay, so that can be generated either from experiment or from pure theoretical analysis or from computational analysis. And CFD or computational fluid dynamics comes under this third variety, which is based on computational methods. Now let us see some brief definitions of CFD here. So it states that computational fluid dynamics is the science of predicting fluid flow, heat transfer, mass transfer, chemical reactions, and related phenomena by solving the mathematical equations which govern these processes using a numerical process. So note this definition carefully as I was pointing out. So this is a science of predicting fluid flow, but it doesn't stop here. It also involves heat transfer, mass transfer, chemical reactions, and related phenomena by solving mathematical equations. Mathematical equation means governing equations, so that we generally generate by our concept of conservation laws. Okay, and which will govern this process using a numerical process. Okay, so numerical process is the backbone for these techniques. Okay, so this is general definition. Then it can be also casted in this way, that it is a methodology for obtaining a discrete solution of real world fluid flow problems. Okay, so this is a discrete problem. So this means this discrete solution means this is not a continuous solution you will not get. I will explain it. Let me cover this point also. So what do you mean by this discrete solution? The solution is obtained at a finite collection of space points and at a discrete time levels. Okay, so discrete time levels, that means, so if you have a pipeline like this and you like to study this pipeline flow where some fluid is entering from here and it is getting out from other side, so you will not get continuous thing. So what the approach is that you will get the results at some discrete points. At a particular points you can get the solutions. Okay, so this is why, although this is a continuous domain, you are getting the results at some points. And if you so what we do generally, these points we consider at a very close distance so that it appears to us as a continuous. Okay, or you can extrapolate or interpolate between these 2 points to get the data from any intermediate points. So we are not going to get any continuous profile. We will get instead at a values at a discrete points. Okay, and if these points are very close to each other, it appears to us as a continuous point. So we will show some results at the end, so that you can understand this concept in a better way. Okay, so this is what CFD is all about. Okay, so it is a science for predicting fluid flow, heat transfer, mass transfer, etc., by solving the governing equation numerically. Okay, so this is all about, and we will generate the data at some discrete points rather than producing a continuous solution. Okay, so this is all about CFD can be defined in a brief manner. Now, after understanding what is CFD, let us see why to use CFD. Okay, so why it is so important and what is why we should think on it. So there are we can answer these things. Why use CFD in two ways. So first one is for analysis and design of engineering problems. Okay, so analysis and design means the first thing is that simulation based design instead of build and test. Okay, so earlier approach, so before 1980s or so, when computer was not there, so most of the approaches was that you, based on your experience and intuition, you build something and test it. Okay, so if you like to develop some prototype or some new system, you just build it and test it. If it doesn't work, then either modify it, and it was a time taking and cost expensive matter. Okay, so this is simulation based design means, so before developing or building that prototype, you can generate it in a computational environment and you can see its advantages, disadvantages, and its different properties. So that actually makes the process cost effective and more rapid than experimental fluid dynamics. Okay, so rather than build and test, you can do the simulation first. You can get an idea that what can happen in such a design, and then you can go for the design. So it makes the process rapid and cost effective. Second point is that CFD provides high fidelity database for diagnosing fluid flow. Okay, so if you like to understand or investigate or analyze a particular fluid flow domain, so it can give you a detailed data set. At each point to point data you will get. Okay, so if there is some turbulence, there is some shock wave is generated, everything you can see there from the database. So that is the necessary guide for a better design and analysis of a system. Then simulation of physical fluid phenomena that are difficult for experiment. So first one, so this thing is talking that where experiment is possible, but still in order to shorten the time and reduce the cost, you can go for simulation based design. But there are another set of things where actually you cannot do experiment. Okay, there are systems or suppose in microgravity applications. Okay, so what will be the heat transfer, for example, in a spacecraft? Okay, so can you do experiment here? It is not possible because generating a microgravity setup is almost impossible on Earth's surface. Okay, so that is an extreme setup. So similarly, there are some phenomena which are very dynamic in nature, like let's say film oil. Okay, or even boiling at a vigorous scale. So your interface will be so dynamic that it is sometimes difficult to catch them experimentally. So some cases like full scale simulation like ships, airplanes, so you cannot do experiment with them. You cannot build a seat for your experimentations, right? So that is not possible. Similarly, environmental effects. So wind, weather, okay, so how a cyclone will move, okay, so how it can impact a particular zone, you cannot do experiment. So these are some regimes where experiment is not possible. Similarly, hazardous, say explosion, radiation, pollution. Let's say one chemical plant, there is some accident happened and some toxic gas are released. Okay, so how to do, you cannot do experiment with such situation, right? So you need to rely on some analysis, so on some either theoretical analysis or some computational analysis. And then there is some physics like planetary boundary layers, stellar evolution. So these are astronomical cases which you cannot, you can never dare to do experiments. So these you need to take the help of theory or simulations. So that's why where this kind of CFD approach can be taken. Okay, so two aspects, one is analysis and design, and one is where experiment can be done, but use of CFD can make the process faster. And there are some situations where experiment cannot be done. So CFD will be the route only available to you. And second thing is researchers' point of view, that knowledge and exploration of flow physics. Okay, so there are many fluid flow domains are there where many interesting feature can take place. Okay, and if you like to generate knowledge about it, so for example, there is a porous media flow. Okay, so porous media flow is a very complicated process. Okay, so till date the theory is not properly developed. So you can explore, you can do research, you can generate knowledge, you can understand the flow physics. So that is a research purpose you can use. Okay, so in most of our academic institute, people use this CFD for understanding lot of problems which is unknown to us. Okay, so that is another aspect that we should use this CFD. Okay. Now this is also similar to that line. What are the benefits of using CFD? Because it will help you to get insight of the process. Okay, so where difficult to prototype or test through experimentation, or you can get better details. Okay, so you do not know what is happening inside a reactor. Okay, so if it is a polymerization reactor or high temperature, high pressure reactor or fluidized bed reactor, so you just design it, but no one knows that what is happening inside internal picture. Even by experimental probes also, it is difficult to get a detailed picture of the internal dynamics of a reactor. But if you can do proper CFD analysis, it is possible that you can get the temperature, velocity, the species concentration at each point of the inside of the reactor. Okay, so that it will help you. Then you can get CFD helps to do some foresight, get some foresight. Like it helps to predict better. Okay, so predict the situation. So how can be the prediction in a shorter time? So that is possible by CFD, and it can help you to get more efficiency of the process. Like it can help you design better and faster, economical, meet environmental regulations and ensure industry compliance. Okay, for example, in automobile exhaust, so you have a heterogeneous catalyst bed there, right, for trapping sulfur oxides or nitrogen oxides. So what can be the arrangement of that particular the catalyst bed? Okay, so that can be generate with a less pressure drop, can trap most of the pollutants. So these kind of designing applications you can enhance the efficiency through the CFD analysis. It can lead to shorter design cycles and your products get to market faster. So you know that products from R&D to market, there is a long chain. Okay, so each step there is some process. So if you can do proper CFD analysis, so it can reduce that time period. Then in addition, equipment improvements are built and installed with minimal downtime. CFD is a tool for compressing the design and development cycle, allowing for rapid prototyping. Okay, so ultimately the whole process of product development or process development becomes more efficient. Okay, so if you use proper CFD analysis, and that's why a lot of industries are right now interested and they are trying to do some CFD analysis before optimizing their design of equipment or process. Now, after seeing that its benefit and its advantages, let us see that where it is used. Okay, where it is used, that we will discuss in a few slides. Okay, so so I will point out few sectors where CFD is highly deployed. Okay, and first of the foremost thing that I like to mention is the aerospace industry or aeronautical industry. So even if you search for CFD jobs, okay, so in any of the job profile, you will see that throughout the year, there will be some post, some vacancy will be there for CFD engineers, where from the aerospace sector. Okay, because aerospace sector is a very capital intensive sector, and it needs development for aeronautical means not only flight, it contains your missile or rocket movement, everything. Means whenever some vehicle is moving through the air, you need to have some data before designing, and that can be generated from your CFD analysis. Okay, so although CFD has two broad classifications, I will tell you later on that it can be broadly classified as compressible flow and incompressible flow. Okay, so you know what do you mean by compressibility, what do you mean by incompressibility, that knowledge, basic idea you are having. So in aerospace application, mostly compressible fluid dynamics is used. Okay, and most of the time mechanical engineers or aerospace engineers are interested in it. Chemical engineers and a part of mechanical engineers are mostly interested in incompressible flow, because in Earth surface, whatever applications we see, mostly we can assume incompressible flow. So aerospace application is a very vital thing where a lot of equipment takes place from this CFD, from the CFD experts. Then comes the automotive. Automotive industry means your four-wheelers, two-wheelers, etc. So you will see that each month all the big companies of the who manufactures cars come up with a new design, okay, new model of car. Okay, and they most of the good companies, they do proper safety analysis. Okay, so what should be the design? Oh, okay, so what can make the movement very smooth? Okay, so here means you will see there are some low cost car. If you run it with at a very high speed, the stability will not be there. Okay, so it will, you cannot control the car. But there are some expensive car, even if you run with a high speed, your stability will be good. So all these comes from the flow factor. I mean, it's flow analysis. Okay, so how fluid flow is. So this schematic diagram, if you see, so you can do such analysis that if fluid flow past this car, then how the streamline, etc. will look like, and accordingly you can do some design change. Even big companies, they do whenever they design some headlight of any car, what should be the shape of this headlight disc and what should be its beam direction. So that thing also can be done through CFD analysis. Okay, so a huge, in a car design part, car manufacturing part, a lot of CFD can be applied. Then comes the biomedical sector. Okay, so this is not only the engineers that only involved, even biomedical or biotechnologists can also use this CFD for understanding knowledge of different part. For example, you can see this figure which state that temperature and natural convection currents in the eye following laser heating. You know, LASIK treatments are there where actually a laser beam is penetrating through the eyes, and this they do some surgery. So how it affects the tear film, that is the small thin film that's present on our eyes. So how it will be done, what will be the effect of that laser beam on that tear film? Okay, how will be the film dynamics will be there? So these are something which you cannot on a living human body you cannot do experiment. Okay, so it is always better to have some prior simulations to get an understanding, and then you can go for its implementation. Okay, so this is some biomedical applications. However, there are many such things. We can discuss some later. Then I will come to next three part, that is chemical processing. And since many students are from chemical engineering background, you know that in process industry there are heat exchanger, there are reactor, and there are pipeline. Those are integral part of any process industry, and everywhere fluid flow takes place at different temperature and pressure. Okay, so for design optimization point of view, each thing you can build up in a CFD environment, and you can see the internal dynamics. Okay, that if there is any dead zone, or if you are if there is any scope of improvement of the process, so that data can be obtained. For example, this picture shows the polymerization reactor vessel and prediction of flow separation and residence time effects, etc. So in big scale reactor, you cannot do trial and error, but if you develop a proper CFD model, you can change it in the computer. You change the flow rate, you can change the temperature, and you can see the effect on the yield finally. Okay, so that is possible. Then there is HVAC type of this backup pressure type of applications where these HVAC applications are nowadays coming up due to the deployment of data center, etc. So where how to uh, uh, design the proper ventilation system of a particular confined environment. So that thing is taken care of. And there is some hydraulics applications. For example, that where the river is flowing, if you are building a dam, okay, so if sudden flood comes, then how much impact it will have on that dam, how much resistance it can offer. So everything hydraulics part, those are comes in the broad category of hydraulics. So that can be tested in any mechanical parts. You know that even the flow of lubricants, there are many parts where hydraulics is important, and you can apply CFD there. Then in marine applications for design of underwater vehicles, okay, so for studying the movement of aquatic animals, and for different sports activity like swimming, etc. So this is the biomechanics comes into play, that how the system can be more improved, or process can be more improved, can be done by proper CFD analysis. Then in the oil and gas exploration, you know that is also a part of fluid flow. You can even you can think of enhanced oil recovery from the porous media and the sea. So everything which you cannot generate knowledge from the experiment can be done through an CFD analysis. And in power generation sector, that how your flue gas will be vented out, what can be its dynamics. So that can also be even in a power industry, thermal power plant, what happens? You can burn coals or any other fossil fuel. So that is a combustion process. Combustion process can be beautifully modeled in CFD. Then that heat is taken by a boiler. Now, what the boiling, different modes of boiling can be modeled in a CFD environment, and uh, you can get lot of knowledge which will help you to make the process more efficient. So these are some areas. The list is very detailed. I am just covering few things to give you the area of applications of CFD. Okay, so after this, so we studied what is fluid dynamics, then what is CFD, what are its advantages, and where it is applied. So for this thing we have discussed. Next part is that let us have a glimpse of the governing equation which are mostly used in case of a fluid flow. Although there are different type of mode equations, but these three are standard equations. So the first thing is continuity equations, which actually gives us the idea about conservation of mass, and then conservation of momentum equations, which is popularly known as Navier-Stokes equations, which is the second one. And the third one is energy equations, that is conservation of energy, thermal energy. Okay, so these three equations will flow because fluid flow is associated with in many cases heat transfer, then energy equation is involved. Otherwise, we can, if we take first these two, if temperature change is not there, not important, then we can consider either continuity equation and momentum equations to solve the problem. Now, this Navier-Stokes equation is a very powerful equation, and it has a huge number of applications, and it is a nonlinear partial differential equations, and it can be simplified based on the situation. Okay, so whatever cases you are taking, you can modify these equations properly, and then you can do the simulations. So in the next class, I will highlight little bit detail of it. Okay, little detail of it, so that this understanding becomes clear before proceeding towards the CFD applications. Okay, so these three equations, so I will not elaborate on these things today, but these are the governing equations. And these Navier-Stokes equations can be obtained from the force balance, from the force that different forces that is acting on a volume of fluid. Okay, so if you like to come up with the concept of Navier-Stokes, you just apply the different forces that is acting on a volume element of fluid, and the force can be classified in two ways. One is on body force, which depends on the mass of that body, and another set of forces acting on the surface, which depends on the total surface area. Now, in the body forces, you will be on the Earth's surface, you will be having always gravitational force, or there may be other forces like electromagnetic force, electric force, magnetic force, etc. Okay, and in the surface force, which is can be classified again by two groups: pressure force and viscous force. Now, viscous force can act on two directions. One is normal direction, another one is shear on this tangential direction, that is shear viscous force. So, if you mathematically model all these force terms and apply it on a particular fluid element, then you will get the momentum balance equations or Navier-Stokes equations. So, we will discuss it in detail in the next lecture. But you just know the different forces which are available in case of a fluid flow. Okay, and these general forces mathematically we need to integrate in the form of an equations, and that we get generally from the Navier-Stokes equation. Okay, so I will not go into further details here, but let me show you the different classifications of CFD problems. Okay, so it starts with general 3D flow equations or flow problems, but it is a 3D problem. But CFD problems can also be, before coming to these, can also come in another two classes. One is called 2D problem, another is called axis symmetric problem. Okay, axis symmetric problem. The difference is that in case of 3D flow equation means you have the three component of Navier-Stokes equations: x direction, y direction, z direction. So total space you are considering. 2D means there are many situations where we can neglect the variation in some particular directions. Maybe z direction or y direction, we can neglect the variation. Okay, so that actually simplifies the case. Okay, one equation if you can reduce, so your computational load will be decreased to a great extent. So in many cases, initially we start with 2D problems. Okay, 2D solution. Okay, so generally instead of, so even if you consider a pipe flow like this, you can simulate it is an you can take an equivalent geometry, 2D geometry like this, a cross section of this plane, and you can analyze that. Okay, so that is possible. So that is for simplification 2D, and apart from that, there are some axisymmetric cases which is some in between 2D and 3D. Okay, where the Navier-Stokes is retained in cylindrical coordinate. Okay, so if your system is in cylindrical in nature, so you can take this axis and take some other spherical coordinate or cylindrical coordinate to get to motivate the equation. So you can get some advantage. You did not need not go to the 3D particularly, but 3D is the realistic figure because we live in a 3D world. Then all these problems can be broadly classified to compressible flow and incompressible flow that I was talking about. So in case of aerospace industry or aeronautical industry, compressible flow is very important because if your velocity crosses a certain limit, the compressibility of air will come into picture. Okay, so that will change the entire dynamics. So that is completely different thing. That is why this is compressible fluid dynamics. And here it can be viscous, it can be inviscous. Viscous means if viscosity is present in that case, viscous force is important, then it is viscous force. If the flow is so fast that viscosity has not any impact, then it can be considered inviscid. That means no viscosity. And it can also be considered as space-time dynamics in the form of laminar and turbulent. And you know what is laminar flow, what is turbulent flow. I'm not repeating that things. Similar thing classifications can be done for incompressible flow. Incompressible flow means water to a great extent in most of our practical application, water or any liquid can be considered as an incompressible flow. Even air up to a certain velocity at a particular temperature can be considered as an incompressible. But if velocity crosses a certain limit, then it cannot be no more considered as incompressible. But thing is that based on this, you need to simplify the Navier-Stokes equation. If it is compressible, then form of the Navier-Stokes will be different. If it is incompressible, the form will be different. So that is why knowledge of the governing equation, that is the Navier-Stokes equation, is very important before starting CFD simulations. So we will spend some time in the next class for that purpose. So this is the broad classifications of CFD problems. Now, what are the basic requirements for CFD analysis? So, as a student or as a practicing engineer, if you like to do the CFD analysis of a particular system, so few things you need to have very clear understanding. So, first is that clear understanding about the governing equations. Okay, G stands for governing equation, especially the Navier-Stokes equation, which is a set of nonlinear coupled partial differential equations. Okay, so you have to have a very clear understanding about the governing equations. So if you are not having any idea, then it will be difficult for you. Okay. Then the knowledge about the numerical methods that is available, especially how to solve IVP, BVP. IVP means initial value problem or boundary value problem. So how to solve the differential equation numerically, that knowledge you should have. Otherwise, there are so many terms that will appear for handling a software, you cannot understand anything. Okay, so this is also important. Then concept of discretization is also important, because the base of numerical methods is that if you have a differential equation, you convert them into a set of algebraic equations. Okay, so that is known as discretization, and this can be done in different approaches like finite difference method, finite volume method, then finite element method, etc. So a lot of things are available. So we will discuss a little bit of finite difference and finite volume in some next classes. So, but this is very important. The concept of discretization is important. So, what do you mean by it? So that thing is you should have clear understanding. Then concept about different types of boundary condition, because boundary condition is very important. The moment you are these are boundary value problems mostly, either initial value problem or boundary value problem. So boundary value problem is, it can be given. So what kind of boundary value problem you should give, that you should know. Because for example, if for a fluid flow in a pipe, you can give a uniform inlet boundary condition, you can give a parabolic inlet boundary condition, or you can give a boundary condition which is fluctuating in nature. Okay, so everything is possible. So you need to know that what are the exact boundary condition that is available in a particular system. Then concept of stability, consistency. So these are some terms which are associated to numerical solution of differential equations. Okay, so stability, consistency, we'll try to cover it up. Okay, in the next classes. And next is programming skill or software skill. So this is a basic need for doing CFD analysis, and a computer is obviously required. Without that, manually you cannot do anything. Okay, because these are ultimately solution of a set of huge matrix. Okay, so a matrix of thousands or lakhs of elements. So that practically is not possible for manual approach. But you need to have a computer in that case. Okay, so these are the basic requirements for doing a CFD analysis: clear understanding about governing equation, knowledge of numerical methods, concept of discretization, concept about different types of boundary conditions, a concept of stability, consistency, programming skill or software skill, and a computer. Okay, so these are the basic requirement. Now the configuration of the computer depends on what kind of systems you are handling. Okay, so it depends on how many number nodes are you are using, what is your system. So depending on that, you need to get the configuration of the computer. So there are some problems which can be 2D problem, which can be done in a normal desktop laptop that we use. But there are some big systems where you need to take the help of either workstation or high performance server, etc. Okay, so that depends on the system size. Okay. So in case of fluid flow problems, pressure velocity coupling is very important. which makes the problem a little bit complex. So in any heat transfer problem, it is very the equation are straightforward. You have a single equation and that you need to solve. But whenever fluid flow is coming, the pressure force additionally comes into picture apart from the velocity component, and this pressure and velocity needs to be coupled in each step. And this particular part for fluid flow, for computation of fluid flow, makes it little bit difficult to understand. And there are some popular algorithms like simple, MAC, etc. So we'll try to cover it at the end. So if you can understand these things, it's very good. Means you are in a good position to start working. Okay, so with this, move to the next one. So what are the tools which are available for using CFD? The CFD models can be created using basic computer languages. So if you know the theory and if you have a good control over your numerical methods, and if you have a good writing skill, good coding skill, then you can write CFD solver with the help of basic computing language like C, C++, Fortran, Python, MATLAB, etc. Any programming language you can use, and you write the algorithms and it can work. But most of the time it is time consuming method, but it gives better control to set the problems according to the specific case. Okay, means solver development by writing is a time taking matter. Okay, so it needs sometimes years of time, or to means not only write, you need to validate it, you need to fine tune it. There are a lot of numerical issues that you need to take care. So by writing CFD code, it is a time-taking job. Okay, but if you can do it, nothing is better than that, because you have full control on your system. Then there are some open source softwares are available. Okay, so open source codes are freely available in internet. One of them, which is very popular nowadays, is known as OpenFOAM. Okay, so if you search in internet OpenFOAM, link you will get, you can download it from there. But you need a Linux environment for that. In Windows operating system, directly it will not work. But in Windows, you can create a user interface of Linux. That options are there. There you can do some work. So we'll discuss it at the end, that how OpenFOAM can be used. Then there are some more codes are available which are in a particular domain. Each of these are important. So this software contains various predefined algorithms which can be used to solve CFD problems. So these are actually comes with a pre-built codes are available. Okay, so you have to choose the particular one and you need to run it properly. So these are free but less documented and have low graphical user interface. So this is free of cost, as you know. This comes free of cost. These are not so well documented. Means you cannot get very detail of it, or this user interface is not so user friendly. Okay, so you need to understand, write lot of things and understand the things. But if you spend some time on this open source code, you have a good flexibility. Then third set of tools that is available for using CFD is the commercial codes. Okay, commercial software like ANSYS Fluent, which is old. It started in 1980s, and then CFX. After that, COMSOL Multiphysics, then Fludyne, Phoenix, Ricardo, CFD. There are so many packages are there. But ANSYS Fluent, CFX, or COMSOL, these are some generalized. Okay. Otherwise, there are so many small packages for particular set of problems. Okay, so that is also available. But you have to buy, you have to get the proper license. These softwares generally contains various fluid flow models inbuilt in it. A lot of material properties are also stored here. To get the solution using software, we just have to select the material, physical model, and predefined boundary conditions. Okay, so some boundary conditions are also defined here. So you need to select that property, and this comes with a generally nice interface. Okay, so you just click the things and it will work. Okay, so these are commercial things. Now it can be used, and it's in fact in academic community, ANSYS Fluent, CFX, COMSOL Multiphysics are very common, very popular across the globe. Okay, so many universities has a license of it. Okay, so this is all about the different tools that is available for implementing or investigating something with the help of CFD. Then I will come to the basic steps of CFD simulations. Okay, so first step of doing CFD simulation is to identify the geometric domain of interest. Okay, this is the step one. You have to identify the geometric domain which you are interested. Okay, so if it is a pipe flow, then you choose the particular segment of that pipe. Okay, or if it is a design of car, then the geometry of the car you need to define it first. Okay, so that is the first thing, you identify the geometric domain which is interested, where you are interested. Then the second step is set the physics of the problem. Okay, so physics of the problem means you need to identify suitable governing equations. So whatever you are going to study, so what would be the suitable equation that you need to find out. So in commercial softwares, these options are given, that steady state Navier-Stokes equation, unsteady state laminar flow equation. So there are varieties of equations are given. So you need to select the proper thing. Okay, so proper even in open source codes also there are you need to call that particular function. Okay, which you like to solve. So you have to identify the governing equations. Okay, this is second step. So first geometry definition, then you need to identify the governing equation, then specify the boundary conditions. Okay, so if it is a pipe flow, you give the inlet outlet boundary condition. What is the wall boundary condition, that is slip boundary condition or no slip boundary condition. So that thing you need to define, that is specification of the boundary conditions. Then fourth step is to specify the material properties. So after defining the geometry, so what will be flowing in the geometry? It is either water, or it is air, or it is some oil. So whatever fluid you are considering, you need to specify the properties. Properties means mostly density or viscosity, surface tension, etc. Now it can be constant or it can change with temperature. So accordingly, you need to specify it, either constant value or in a functional form of that properties with temperature, etc. So that options are there. So you need to identify that. Then select the discretization methods. Okay, after specifying material, you have to select the discretization method. Discretization means the governing equation you have chosen. So that either you apply volume or finite volume method, finite difference method. So what method you like to solve? Okay, so that you need to identify for general, but in softwares, mostly the solver is written in a particular domain. For example, ANSYS Fluent is written with finite volume, COMSOL multiphysics is written with finite element. So it is already written there. Okay, so you need to choose. But if you like to write your own code, you have to find out that what method will be suitable for you. Then specify the solver and run the simulations. Then after that, this solver, there are solver means different algorithms for solving those equations. Okay, and which algorithm you like to choose, that you need to find out, and then you run the simulations. And after that, if the simulation is over, then you need to analyze the results and plot them accordingly. So this is the entire tree process, means entire flowchart of a CFD simulation. So first you identify the geometry. Geometry means this thing. So if it is a pipe flow, you just consider this is as a geometry. Then you set up the suitable. So if it is a steady state Navier-Stokes equation, you just select it. Then you give specify the boundary conditions. What is the inlet flow, outlet flow? What will be the wall boundary condition, etc. Then specify the material, whether water and air. Then discretization method, either finite volume or finite element. And you need to do the geometric discretization of the domain also. Okay, one is the equation discretization, another one is the discretization of the geometric domain. Okay, so I'll come to that later on. Then specify the solver and run the simulations, and finally analyze the results. So this entire process can be shown here in this this diagram here. So first thing is called geometry development. Second is meshing. Meshing means the fluid domain is to be divided into a large number of finite volumes. Finite volume for finite volume method, or finite elements for finite element method, or into number of points in case of finite difference method. Okay, that is the second step. Then partial differential equations are discretized and applied on this particular each of these nodes or mesh points. After that, algebraic equations gathered into matrix which are solved by an iterative procedure. Okay, so this is the solver, and numerical solution gives the values of dependent variables at different discrete locations. So if you develop geometry in this pipe, like a pipe here, then in this particular domain, you discretize this domain into a number of small grid points. This is called meshing. Okay, and each mesh point has a mark. So you have to give some nomenclature I, J, K with the value of x coordinate, y coordinate, z coordinate, and then you select the partial differential equations and discretize them properly using finite difference or finite volume. Then if you do discretize this partial differential equation and apply them on these grid points, you will get a matrix. Okay, so you will get a set of algebraic equations which you can write in the form of Ax equal to b, where A is the coefficient matrix. Okay, and this matrix, size of this matrix will depend on this number of grids. Okay, how many number of grids that you are using. Then you choose the proper method, either Gauss-Seidel or Thomas algorithm. So these are some of the methods which are available for solving linear algebraic equations, set of linear algebraic equations. Then the results, you will get results at each point. At each of these mesh points, you can get temperature, velocity, pressure, etc. after the simulation is over. Now, once you get it, you can do the post-processing part. So this is this part is called your pre-processing. Okay, this is called pre-processing. And after getting the solutions, the result analysis, that is known as post-processing. Okay, post-processing means you are analyzing the generated results, and this is the solution or solver part. Okay, so these three steps broad. One is pre-processing, where you are creating the geometry, meshing it, selecting the partial differential equations properly and discretizing them, and then you are solving. This is solver part, and after that, after getting the results, you do some post-processing to analyze the results. Okay, so this is the entire procedure of CFD. Now let us discuss it little bit. What is preprocessor? So it is the definition of the geometry of the region of interest, that is the computational domain that you need to define. Then creating regions of fluid flow, solid regions, surface boundary names. So this you have to specify. After that, grid generation means meshing. So later on, I will show all these steps individually, taking an example. Okay, so need not worry, but I am trying to give you a broad picture of the overall process of CFD. Okay, so grid generation. So this means the subdivision of the domain into a number of smaller non-overlapping subdomains. A grid or mesh or cells, either grid or cells. Okay, so it can be control volume or control element depending on the process that you choose. Then selection of physical and chemical phenomena that need to be modeled. Okay, so if there is reaction is involved, then you need to take care of the reaction model. So there are, you have to choose that. Then definition of the fluid properties, as I was mentioning, that fluid density, fluid viscosity, etc. has to be mentioned. Then specific and appropriate boundary conditions at the cells. Okay, so these are important. So this entire part is known as pre-processing. Okay, preprocessor. So you have to define geometry, create mesh, select model, give the properties and boundary conditions. So this entire part is known as pre-processing or preprocessor. This is the geometry development part. You can see this is the CAD model of the geometry. This is a pipe flow. You can see it's a pipe bend with an outlet here. Okay, so this is just show you an example of geometry. And you can draw this kind of geometry in a CAD software. Okay, so if you have little bit of CAD expertise, then it will help you to generate in any CAD software, or most of the commercial software comes with some integrated CAD environment. Okay, like in ANSYS, console multi-physics, they all have some CAD environment, so there you can draw it. So you need to spend some time to know that how this kind of geometry can be drawn. Okay. Now geometry needs to be developed in the solver to define the boundary of the system. Two-dimensional or three-dimensional geometry can be developed. So it can be 2D or 3D. For example, the picture that you are seeing here is a 3D geometry. So you can plot a 2D also. Then the geometry can be prepared in different CAD software and imported in the solver. So if you are using some open source code, so you can generate the geometry in some other CAD software and you can import it to the particular that open source code. Okay, so that is possible. Then next part is called meshing. Meshing means the geometry that you have generated, you have to discretize it into small domains. Okay, the flow domains is divided into large number of finite volumes. The accuracy of the solution is dependent on the number of elements in the flow domain. So this is very important. This meshing part is important. We will discuss it later on. That depending on the size of this mesh, your solution, your result will depend. Okay, so how to optimize them? So that thing we will discuss later on. The accuracy of the solution is dependent on the number of elements in the flow domain. Larger number of elements ensure higher accuracy of the solution. However, large number of elements would require larger computational time. Hence, the number of elements should be chosen judiciously to save computational time without compromising the accuracy of the solution. So this we will discuss in detail in further classes because this is very important part. So geometry creation, this is meshing part, and then definition of fluid properties. So fluid properties has to be defined: density, viscosity, specific heat capacity, thermal conductivity, surface tension. So these are the some of the properties. If you use commercial software like ANSYS, then you will be having a text box like this. There you can define the chemical formula or the name of that material, and there is an inbuilt database in this software. So that automatically it can take. And if you want, you can edit them using this edit option, and you can give your own values. Okay, so you can collect the data from any other sources and you can give it. And if you are using some new material, you have to obviously define it. So these are the definition of fluid properties. Then this is boundary conditions. Boundary condition means if this is the domain, this is the mesh domain. So you have to give the inlet boundary condition. You need to give the pressure outlet boundary condition. No slip or slip boundary condition, etc. So this is also important. And then you have to choose the solver. The objective of CFD is to model the continuous fluids with partial differential equations. Okay, so this is the main thing. You have to model the continuous fluid flow with the help of some partial differential equations and discretize the PDEs into a set of algebraic problems, okay, or algebraic equations. Solve it, validate it, and achieve simulation-based design. That is the objective. So you have to discretize that PDEs into a set of algebraic equations. You solve them, and only solution will not work. You have to validate it with some experimental result. Otherwise, you cannot blindly believe the solution that you are getting. So there are some aspects of it. We will discuss it later on. And discretization methods are finite difference, which is straightforward to apply, simple, and structure gives are generally used. Finite element has advantage of the geometries. It can use any geometry. Any complicated geometry can be modeled by the help of finite element. And finite volume has an advantage of conservation. Okay, so it can conserve the properties properly, and any geometry can be chosen. Now, finite difference method is very straightforward to understand. Okay, and however, for fluid flow problem, in most of the commercial softwares or open source software, you will see that finite volume is adopted because it has some inherent advantages. Okay, so in next classes we will see that the difference, how with the finite difference, which is easier to understand. We will see that first, and then we will see that how it is differ from the finite volume method. Okay, so that we will see. This is all about the solver, and now comes the post-processing part. Post-processing means once you get the results, you need to see that, right? See that results. That is, you need to use the versatile. You have a lot of data visualization tool. Okay, so generally CFD results means it is a set of data. Okay, different values of velocity at different points. So it is a set of data only. So that you need to plot in proper visualization tool, and then domain geometry grids display that you can see, vector plots you can see, line and shaded contour plots, 2D, 3D surface plots, etc., particle technique, etc. So many things can be done. So I'm not going into this all the details. Just to show you some of the examples. And this is an example of vector plots which is obtained from a ANSYS fluid simulations. So you see that this is a flow domain where fluid flow is taking place around this object. Okay, this is an obstacle, and how the flow vector velocity vectors can be plotted, that is shown here. Similarly, here also you can see in a proper geometry in a pipeline, bed pipeline, how velocities can be shown. Okay, and color indicates the magnitude of these velocity vectors. Okay, so this is just to show the post-processing part. Many times you can see contour plots. Contour plot means the color diagram. Okay, based on the values of the vectors. Like this is a flow channel where fluid is entering from this direction, and it is moving in a buffet tank like this. It is moving out. So how the velocities and what are the at what zones what the velocities are there for the fluid, that is shown in this particular thing. So these are called contour plots. So in CFD results, you will see lot of contour plots and this kind of vector plots, and this gives us lot of understanding. So with this, I will now show few case studies. Okay, case studies means some reported case which people have done earlier and they have published it. And let us see that to give you a feel that what kind of investigation can be done with the help of CFD. So this is a paper of chemical engineering science in 2020. It was published. So it shows that implications of hydrodynamics on the design of pulsed seep plate extraction. You know that seep plate extraction columns are there. Okay, so if you have studied mass transfer course, you must have seen this kind of column design. So here, what will be the internal picture of that species concentration? Okay, so what will be the velocity field? So these particular figures are showing the velocity field at different positions. Okay, at different time instant or different positions, this is showing. Okay, these are the contour diagrams. This red color indicates a particular velocity, green is indicating some other velocity. So this is also from the same paper. It is showing that some this plot of instantaneous volume fraction. So this is the plot of volume fraction inside that reactor. Look, in this kind of column, data like this you cannot generate from any other approaches. Okay, either theoretical analysis or experimental analysis will not give you such a detailed picture. But here you see that each point what should be the volume fraction, where it is gas is higher, where it is liquid is higher, everything is very clearly depicted. Anyone has opened their mic, I think can. Please, someone is unmute yourself. Okay, yes, okay, now it is okay. Okay, so this is one example, and then CFD is not only important as is for the engineers, it is also equally important for the clinical persons also. Okay, there are so many, because our body is full of fluid flow, fluid dynamics. Okay, so air is flowing, blood is flowing, entire system is fluid mechanics basically. So knowledge of exploration of flow physics by real-time visualization using graphical interface. Okay, so this is your respiratory system. Okay, so how air is entering into our respiratory system and it is going to the lungs, etc. So if you like to get an idea about the entire flow profile, you can do fluid analysis, the CFD analysis. Okay, so that will give you this kind of contour mapping and show you the streamlines that how flow is taking place. So this is a paper which was published, review paper. It states about computational fluid dynamics. Just 1 minute, I need to take a call. Oh, sorry. So this is a paper of computational fluid dynamics modeling in cardiovascular medicine. Okay, so to see the efficacy of a cardiovascular medicine, you need to understand the entire velocity profile in our heart and associated veins and etc. So that entire thing can be modeled like this, and in some of the European universities have a specific subject called cardiovascular fluid mechanics. Okay, so they teach it and they like to simulate it. Okay. Then this is a CFD study of single phase and multi-phase pump mixture, analyzing design parameters, flow structures, and turbulence. Okay, so this is how you can generate. This is a start tank sort of thing, as you can see, and you can see the flow profile that is captured by experiment. This is the experimental data, and you can match the same results with the simulated data. These are simulation data, CFD-based simulation data, and you can get the entire flow structure of the domain. Okay, so these are the top views at different cross sections. Okay, you can see that impeller blades here, and surrounding the blade, how the fluid is moving, that you can get. Right? This is also the internal picture of the fluid flow. And this helps as a design engineer or as a process engineer, if you know these kind of things. So whenever there is some problem, it will help to sort out that things. Okay, so you can understand. So this entire knowledge of fluid flow inside this domain would be helpful for you. So this is a snapshot for CFD simulation of a fluidized bed reactor. Okay, so in the this shows that how the volume fraction is changing. Okay, so this is also taken from a particular paper. And this is temperature distribution over a multi-tubular solar reactor for hydrogen production. Okay, so the paper references are there. So just to show you the applications that what can be done. In the right hand side, it shows in fuel cell. Okay, so this is also a temperature distribution in a fuel cell that is shown here. This is for a chlorination contact tank geometry. Okay, and some of the other things I'm not going into detail. This is one of my work which was related to film boiling. Okay, at a very high temperature with saturated water, and we have shown different kinds of regimes of boiling. So this can be done for investigating. But yes, this is very important. Be careful and do remember that CFD is not colorful fluid dynamics. Okay, because it generates lot of colorful result. Okay, so contour plot looks very good to us, looks attractive to us, but you should not rely them blindly. Okay, it is computational fluid dynamics. The results, whatever you are getting, you have to be very careful about their reliability. So in many times commercial softwares you use, you just directly give some input, some output you are getting, and you can think that this is what it is happening, but it may not be true all the time. You need to validate it properly. You need to check the effect of grids on that study. Then only you can say that it has some kind of reliability. Okay, so that is how the solver needs to be established. Okay, so it has some limitations. Okay, CFD can't do anything. Okay, so it can reveal to a great extent based on the model, but if the model has some limitations, model equation has some limitations, then that cannot be overcome. Okay, so you have to be very careful about it. So with this, I will now give the first assignment for the students. Okay, those who want to like to learn it. You try to install the student version of ANSYS Fluent, which is free. Okay, so if you go to the ANSYS Fluent website, I think for a 1 year or 2 year, it remains valid. So if you register with a student account, you can download it and you can check if it is working. Just do this part and wait for my further instruction in the next class. Okay, which will be scheduled in the next Saturday. Okay, so with this thing, I need to stop right now because it is already 1 hour 45 minutes. Better to stop right now. So next, I take start from here from the next class. Okay, so let me stop here, but I'll be happy to take any questions if you have at this moment of time.
So can I ask?
Yes, please go ahead.
So you said that the CFD results that we have got, we have to validate it with experimental results. So sir, if
Yes.
we could like experiment only, then why use CFD? Like
No, no,
like
no. And let me clarify that. Why? That's a good
yeah.
question. Actually, that I am trying to emphasize that experiment has limitations. That's why you are doing. And again, I am telling you to do that. The reason is that whenever you are writing or developing a new code or new solver, okay, so numerical analysis has some certain errors. Okay, errors are associated with it. It is not truly that. So, what is the standard approach? You first test your code with some known results. Okay, so before attempting any unknown problems, you apply that solver or that code to some known problems. Okay, which are well explored by experiment. Correct, experiment or other analysis or other theoretical analysis. Some standard case studies are there, standard problems are there. So first you start validate your code with those known results. Okay, which are already established. Now, once that is done, that whatever you are getting, the experimental results is saying the same thing. That means your code is validated. Now, or based on that validated code, you can do some prediction to some unknown problems. Clear? So, but out of something you have written your own code and you cannot rely that things. Okay, so that is difficult. You have to find out some similar situation where experimental results are available. So you try to validate your method with that thing.
So,
Okay,
sir,
then
say,
you will go. Yes.
yeah, say I'm trying to design a distillation column. So a
Mhm.
distillation column is huge. So
Mhm.
I mean, where do I get the data for that? Like I'm designing a whole new distillation column, and let's say I'm also trying to add a
You need to be very careful about whenever you are thinking of the entire setup. Distillation column can be analyzed by CFD in different approaches. Number one is that it depends on that how much accurate data you want. For example, there are distillation column if it is a tray type of column, different plate columns are there, plate trays are there. Then if your interest is to know that how the gas mass transfer is taking place from liquid phase to gas phase at a particular plate, then you did not model the entire column. Okay, you choose the section of the particular domain carefully and you model that part. Okay, try to get the results because the upper or bottom columns may have some change in the efficiency of what, and you can do that extrapolation part because entire column simulation means it's a big thing, means you have to handle huge number of nodes. Okay, which will be very difficult computationally handle. So you have to be very judicious about the selection of the domain. Okay, now if so distillation column doesn't means I cannot go at a stretch means for look, for mass balance or energy balance, if you like to get idea about that if I change some flow parameter at the inlet or feed, what will be my impact on the top and the bottom product, then you need not do CFD analysis. You can do simple mass balance, energy balance, which can be done in your software like Aspen Plus, right? So that will give you. But what Aspen Plus will not give you that what is happening in the internal side, inside of the thing. Aspen will not give you the internal picture of the distillation column. Okay, so if you like to know that how fluid is flowing in the inside of tray, okay, how gas exchange is taking place, okay, so whether I change the design of that tray from a particular one orientation to other orientation, okay, so what will be my impact? So that probably Aspen cannot give you. So then you need to come to the CFD part. Clear?
yes.
So you need to be very specific to the problem that what you want. Okay, accordingly you need to choose the regime of the simulation.
Yes.
Okay. Any questions? Any more?
The participants, if you have any further questions, you can ask, sir, on today's class.
Okay, this is an introductory class and I just tried to give you the broad picture of CFD. Okay, so
Yes, sir.
you just There may not be so much questions now. Maybe in next class onwards, when I will discuss the technicalities little detail, then questions may come up. However, think on it. Okay, to those which it is a new subject, think on it, and later on I can share some notes, etc. You can study that thing. Okay. So if there is no more questions, you can stop for today. Next class will be next Saturday. Timing will be intimated to me.
So next class will be tomorrow, sir.
Tomorrow, because tomorrow I need to travel. Okay, so I will not be available. I have informed them.
Okay, sir.
So please reschedule it
Okay, sir.
next Saturday 2 class, first half, second half. Okay.
All right, sir.
Okay, sir.
Okay. Okay.
Thank you, sir.
Okay. Thank you. Thank you
Thank
very
you,
much
sir.
for your attention.
Thank you, sir.
Thank you.
sir.
Thank you, sir.
Thank you.
sir.
Thank you.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.